Alrighty, the plan now is to motivate an exploration of integration beyond that of Riemann. So in Calculus 1, you define Riemann integration, you integrate continuous functions. In Calculus 2, you integrate over discontinuities. You integrate over vertical asymptotes, for example. Sometimes the integrals diverge, but you give meaning to integrals of discontinuous functions. So a reasonable question is, when is a function Riemann integrable and when is it not? That is, give me a classification of the condition of Riemann integrability for a function. And that's what we're up to in the Riemann Lebesgue theorem. So our motivation here is, why would you want to go beyond Riemann integration? And we'll give two reasons for that. One, somewhat theoretical. You get a big advantage by having Lebesgue integration in terms of some limit behaviors of functions. It's a lot more well-behaved than Riemann integrals are in terms of limits of sequences of functions, to be elaborated on at the end of this presentation. And we want to, as I said, classify when a function is Riemann integrable and when it isn't. And see the limitations of Riemann integration and say, well, I want to integrate more functions than those, but it's going to require something more than Riemann integration, and that's where the Lebesgue integration comes from. So these notes are really from my senior level analysis class. They're from the book by Kirkwood that I've mentioned before, An Introduction to Analysis. And our setting here, because we're dealing with Riemann integration, is that we have a function f, a bounded function on a closed and bounded interval from a to b, because that's where all Riemann integration starts. That's where it starts in Calculus 1, and that's also where it starts in an analysis class. From there, we can do other things with those. For example, you define improper integrals over infinite intervals as limits over finite intervals. So this is where Riemann integration begins. So that's our setting. So this isn't some special restriction on function f. This is the kind of functions you, at the base level, that you integrate in a Riemann sense. So bounded functions on closed and bounded intervals. Okay, so we're following, this is out of chapter 6 of Kirkwood, and we'll give necessary and sufficient conditions for such a function to be Riemann integrable on the interval from a to b. So what we'll do is review what it means to take a Riemann integral, and we'll do it in an analysis class style versus doing it just in a Calculus 1 style. Basically, in here, we'll be dealing with soups and imps of function values. And what you did probably in Calculus 1 was motivated by maxes and mins, inscribed and circumscribed rectangles based on function values. So our stuff here, just out of senior level analysis class, it ought to be a little bit more mature. So we'll start with a partition P of the interval a, b is a finite set, x sub 0, x1 through x sub n, where a equals x sub 0, b equals x sub n, and we have these other x values distributed in the obvious order. And we'll define, ultimately define Riemann sums based on partitions. So let x sub I minus 1 and x sub I be elements of a partition. So they're the little endpoints of these subintervals that we'll introduce. For f bounded on the interval from a to b, define the following. Lowercase m sub I of f and uppercase m sub I of f. Lowercase m sub I of f is the infimum of f of x, such that x is from this little subinterval x sub I minus 1 to x sub I. For capital M sub I of f, we define that as a soup of function values from x for x from that subinterval x sub I minus 1 to x sub I. I'd like to say, all right, so this is a maximum function value and this is a minimum function value. But I don't know, we got maxes and mins. If we had a continuous function, we would have maxes and mins. By the extreme value theorem, we would have a continuous function on these little compact sets, these little closed and bounded intervals. But nobody said nothing about anything in terms of properties of function f other than it was bounded. So it's a bounded function on a set interval from A to B, but no properties about continuity in particular. So I can't say max and min. Are you worried that I can't say inf and sup? We're okay on that one because what we're looking at is, in both cases, we're looking at sets of function values. Well, you know, we've hypothesized that we're dealing with a bounded function. Okay, so this is, in this case, this is a set of real numbers that's bounded below. So it has a greatest lower bound. That is, it has an infimum. This is a set of real numbers that's bounded above. So it has a least upper bound, a sup. So these really are defined using the axiom of completeness there in establishing that, in fact, these two parameters really are defined. And also define, this looks very calculus one-ish, define delta x sub I to be x sub I minus x sub I minus 1. Of course, you think of these as introducing little subintervals. It's the length of the ith subinterval is what it is. Okay, so we're going to set up upper and lower Riemann sums. Kind of should have seen that coming. The notation is a touch exotic. So we're defining S overline F semicolon P to be an upper Riemann sum. Upper, so that's why there's an overline. Over here we got an underline when we look at lower Riemann sums. It's a Riemann sum because it's basically base times heights, though the height is taking a touch more abstract role here. But we've got this number based on function values. It's the sup of function values when x ranges between x sub I minus 1 and x sub I. I'd like to say it's a maximum, but I can't for reasons just discussed. But it's related to that idea, I suppose. Then times delta x sub I. So upper Riemann sums are these sups of function values times delta x sub i's. Why? We could certainly interpret that as an area of a rectangle. It's a base times height. The base is a usual thing, delta x sub I. Well, that's just the width of that ith rectangle. The height isn't necessarily a function value, but as always, the height's based on function values. Based on them, based on these function values, in fact, in this way, in this sup way. Lower Riemann sum of function f with respect to partition P is similarly defined, except now we use the infima, the lowercase m sub i's. And these are also rectangles. There's the base, and the height is based on function values in this sense. Function values, and this time an inf. All right. Now, if this function's continuous, and nobody said it is, but if it was, for these little partitions, if these intervals are small, then the input values are close together. I'd expect these output values to be close together. So that'll play a role in establishing part of what we're going to prove, the Riemann Lebesgue theorem. But as is, we're using these sups of function values and infs of function values and setting up upper Riemann sums and lower Riemann sums of function f on interval a, b with respect to partition P. When you did this in Calculus 1, you chose a particular x value and you fed it into the function to determine the height. A common notation is to take x sub I star from this little subinterval. Here it is, this little subinterval, take an x value, call it, say, x sub I star, Plug that in the function and use that to determine a height. Now that's some ambiguity there because you don't know how that x sub I star was chosen. These are both unambiguous. You give me the partition, the rest of it's determined. You give me the partition and the function, and the rest of this is determined. Upper and lower Riemann sums defined as given here, totally unambiguous. All I need is a partition and a function. We, of course, will somehow or other take limits and turn those Riemann sums into Riemann integrals. Okay. This is rather similar to a calculus 1 style, where it says in the notation above, take x sub I bar, the x sub I star I was talking about. That's the way our calculus book deals with it here at ETSU at least. But take an x sub I bar to be an element of this interval and plug it into the function. All right, that produces a Riemann sum. All right, I can't call it the Riemann sum anymore because I don't know how you chose that x sub I in that interval. We could have chose left-hand endpoints, right-hand endpoints, midpoints, or common numerical technique to use in numerical integration. But this is called a, that's maybe the most impressive word, a Riemann sum. A Riemann sum because I don't know how you chose the x sub I bars. A Riemann sum of function f with respect to the partition. Above we had the upper and lower, the upper Riemann sum and the lower Riemann sum because all I needed was the partition there. Here it's a sum of a particular type. Are upper and lower Riemann sums actually Riemann sums? Well, they are if this is actually a function value and if this is actually a function value, and they might not be. Remember, they were sups and nths of function values. They may not themselves be function values. I bet you they are if we have a continuous function, and continuity plays a big role in what we're up to here. But an odd thing, upper Riemann sums and lower Riemann sums, depending on the function, may not themselves be Riemann sums in the sense defined here. Well, anyhow, with the notation above, we're going to use the upper and lower Riemann sums to define upper and lower Riemann integrals. So with the notation above, define overlined S of f to be the infimum of all overline S, f semicolon p's, such that p is a partition of the interval from a to b. So what you're doing is you're taking all of the upper Riemann sums and taking an infimum of them. Down here, we're taking all lower Riemann sums over partitions is what the sup and inf are doing, and taking a sup. Now, does that make sense? Well, it ought to make perfect sense. When I look at what we get, say, with an upper Riemann sum, we're using suprema of function values. Well, that's, I want to say, this is the biggest that the function gets. How about this? It's an upper bound. It's a least upper bound, but it's an upper bound of the function values as x ranges over this interval. So it's, it's too big maybe for some of the function values. These up here, we did an infimum. These are too little, too small, they're less. I need to use the inequality idea more instead of big and little. But I'm underestimating here and I'm overestimating here. When I find the areas of those rectangles, well, the function may have less area under it than what we're getting when we do computations like this. Point being, just as maybe in Calculus 2, when you looked at inscribed and circumscribed rectangles, we're overestimating with an upper Riemann sum, and we're underestimating with a lower Riemann sum. All right, how are you going to make those approximations better? Well, the way you do it in calculus is you make the partitions really fine You take a limit as the norm of the partition goes to 0. Here, what we're defining deals with all partitions, in particular, those that are really fine. They don't have any big pieces left in them. It's all partitions, but what we're doing is have an eye on the partitions that are small in norm. It says all partitions. And you knew the upper Riemann sums kind of overestimated the area. Okay, we'll shrink them by taking an infimum. I knew the lower Riemann sums underestimated. Okay, we'll take a sup then and sort of swell them up. So that's the idea behind taking the infimum of the upper Riemann sums and the supremum of the lower Riemann sums. And these result correspondingly in upper and lower Riemann integrals by definition. You think they're going to be the same, the upper Riemann integral and the lower Riemann integral? Well, it depends on the function. Hopefully so. If they are, then we're in business as far as Riemann's concerned. So the next definition says, let f be a bounded function on the interval a to b, closed and bounded. Then f is said to be Riemann integrable on that interval if the upper Riemann integral and the lower Riemann integral are the same. In this case, that common value, say the upper Riemann integral, is called the Riemann integral of the function over the interval, and it's the usual notation, integral from a to b of f of x dx. I've actually followed notation out of the senior level book, and they've written this as an integral from a to b of f. They leave the of x dx stuff off. I'm okay with that, usually. We'll be doing a lot of that in here. A passing comment, we'll be using this notation, but we'll be using it for Lebesgue integrals, not for Riemann integrals, because we're all about Lebesgue integrals. So take with a grain of salt this particular set of symbols. It's just the usual integration that you did in Calculus 1. All right, something you didn't do in Calculus 1 was figure out which functions are Riemann integrable, for which functions does this property hold, and which functions are not Riemann integrable. Okay, so what we want to do is put some conditions, necessary and sufficient conditions, on a function to state whether or not it's Riemann integrable. So I could just pick the function up and look at it, whatever properties it has, say, oh yeah, that one's Riemann integrable, or that one ain't Riemann integrable. We're going to state a few results that are not of that nature. First, let's explore some conditions related to the integrability of f on the interval from a to b. These conditions, they're not that impressive. They're merely restatements of the definition of Riemann integrable. The proofs will follow from the definitions along with properties of sups and ints. The first is the book I took this from calls it the Riemann condition for integrability. Yeah, it's most unimpressive. Let's talk about why. A bounded function f defined on the interval from a to b is Riemann integrable on a to b if and only if, sounds good so far, for all epsilon greater than 0, there exists a partition p based on epsilon of the interval ab such that the upper Riemann sum of f with respect to that partition minus the lower Riemann sum of f with respect to that partition is less than epsilon. All right, I like the if and only if part. Here's what I don't like. It doesn't say anything about properties of functions f. All they've really done is taken the definition of Riemann integrable, and remember the definition of Riemann integrable was that the upper Riemann integral and the lower Riemann integral are the same. The upper Riemann integral was defined as an inf, the lower Riemann integral was defined as a sup. In setting these upper and lower Riemann integrals up, maybe I should observe somewhere along the line, was implied by what I said. The upper Riemann integrals are always greater than the upper Riemann sums for a given partition are always greater than the lower Riemann sums. So if I take an upper Riemann sum minus a lower Riemann sum, the smallest I can get is 0. So I said these overestimate and these underestimate. All right, so we'll always have these bigger than these. All right, so how could I have the upper and the lower equal? Well, they'd be equal if I can make these arbitrarily close to these. And remember, these are bigger. If these are all bigger, the nth of these are bigger. And if these are all lesser than the upper Riemann sums, then the sup of these is lesser. So I could also draw the conclusion that the upper Riemann integral is bigger than or equal to the lower Riemann integral. So if something goes wrong, it'll be this is bigger than that in terms of Riemann integrability. But the nth and the sup, man, those are basically limits. So I'm saying in some sense, take this with a grain of salt, I'm saying what I'm saying. I'm just trying to give you a feel for this stuff. That, you know, when the partitions are like really good, really fine, maybe, then these two things are close together. They have to get arbitrarily close together so that in a limiting process, we get equality when we do the nth and the sup thing. And as it says before the statement of this, the proof of this, which I don't want to get into because there's not much to be learned there, simply involves the definition of upper Riemann sum and lower Riemann sum, and the definition of sup and nth, the definition of upper Riemann integral and lower Riemann integral in terms of sups and nths. So there's your necessary and sufficient condition for Riemann integrability, but it's just not useful. All it does is take the definition we already had and word it in terms of epsilons instead of sups and nths. So let's see if we can't do a little better than that. No, it's actually first, let's mimic what you do in calculus. Here's another one I'm going to complain about. Let P be a partition of the interval A to B. The norm, sometimes it's called mesh. That was a word used, I think it popped up in the 80s when I was first teaching calculus. I don't think it's a very common word to use in connections with partitions these days. Norm, I think, is a more common word. It was in the 80s as well, but this was an alternative word for norm of a partition. The norm is simply the biggest delta x sub I. It's the width of the widest interval determined by these little points when partitioning up the interval A to B. I can say maximum and not sup, right? Right, there's only a finite number of them. Partitions are finite partitions by definition. So the norm of a partition is the size of the largest subinterval determined by that partition. And if you'll think back to calculus 1, having big bases to rectangles, that usually leads to bad approximations. So big norms are bad. If we have little norms, that means all of these little subintervals must be little. So making the norm small means the estimations in terms of Riemann sums will be better approximations to actual integrals. And that's sort of what the next thing says. Bounded function f is Riemann integrable on the interval from A to B if and only if for all epsilon greater than 0, there exists a delta greater than 0 such that if P is a partition with the norm of P less than delta, then upper Riemann sum minus lower Riemann sum with respect to that partition is less than epsilon. It's got epsilons, it's got deltas. Well, that sounds just like a limit. A limit statement. There's epsilons, there's deltas. I don't see x's and y's. I see partitions and Riemann sums, but it is a limit. In calculus 1, you might define the Riemann integral as a limit as the norm of the partition goes to 0. And that's exactly what we're doing here. Limit as the norm of the partition goes to 0 of Riemann sums. Yields the Riemann integral when the Riemann integral exists. Again, that don't tell me nothing about function f. That tells me stuff about partitions and Riemann sums. I want a classification of the Riemann integrability of a function in terms of properties of the function, not in terms of all this partition stuff. Because I can't pick up a function and tell if it's Riemann integrable if I got to go through all this partition stuff. I want a property of the function. Okay, so let's go all the way back to calculus 1 and prove that continuous functions are Riemann integrable. Now, I ain't doing this just for fun. Continuity's got a lot to do with the result we'll state. Functions that are continuous are Riemann integrable. But some functions that are discontinuous are also Riemann integrable. You did that in calculus 2. Well, how badly discontinuous can they be and still be Riemann integrable? That's what we're trying to figure out. And the answer you didn't do in calculus because it involves measure theory. The answer you may not have even done in your senior level analysis class. One reason I like this Kirkwood book is it has this result in it. So the following result is shown in calculus 1. In fact, all functions encountered in this setting of integration in calculus 1 involve continuous functions. So you don't even deal with discontinuous functions in calculus 1. You do in calculus 2, though. You do in some of the generalizations. And they're all based on bounded functions on compact intervals. Technical difficulty here. I'll abandon my sunscreen. All right, so let's prove if f is continuous on the interval from a to b, then f is Riemann integrable on the interval from a to b. Continuity implies integrability. Okay. Suppose f is continuous on the interval. This is a compact set, so continuity of a function on a compact set implies uniform continuity. Ring a bell, the analysis ramped up pretty fast there. But a function that's continuous on a compact set is uniformly continuous on that compact set. All right, we need the uniform continuity to establish the result. So let epsilon be greater than 0. By the uniform continuity of f, that means there exists a delta based on epsilon greater than 0 such that if x and y are any elements of the interval from a to b, that's the uniform part, and the absolute value of x minus y is less than delta, then the absolute value of f of x minus f of y is less than this positive number. All right, regular old continuity at a point says fix a point. If I choose other values close to that point, I get function values to be small. So I can make differences of function values about a point as small as you like by making the input values, the x and y values, sufficiently close, about maybe a fixed point x. Here, I don't fix the point x. I say x and y can be anywhere in the domain of this function. They just need to be close together. The anywhere in this interval, that's the uniform part of uniform continuity. So if x and y are in the domain of the function and within delta of each other, then the corresponding function values are within this thing of each other. I choose a positive number. For some reason, I chose epsilon over b minus a instead of just epsilon itself. B minus a, that's the length of that interval. I bet that's going to play a role. So what we're saying is if x and y are close together, then f of x and f of y are close together in a usual epsilon delta type sense, well in the setting of uniform continuity. Okay, so here's how we're getting into this. Let P be a partition of the interval from a to b such that the norm of P is less than this delta value. So what that means is, if we look at the interval x sub I minus 1 to x sub I, how big is that interval? Well, it's x sub I minus x sub I minus 1. What's the norm of a partition? It's the maximum of all of the lengths of the little subintervals. This is one of them. So the width of that little subinterval is less than or equal to the norm. and strictly less than delta. So if I choose any two numbers out of that little subinterval, those two numbers will be less than delta distance apart. This will be satisfied if I choose x and y from any of these little subintervals by the choice of the partition. We made it sufficiently fine so that that occurs. Ooh, and if you get the input values close together, I know what's going to happen with the output values by the uniform continuity. Okay, on this subinterval, x sub I minus 1 to x sub I, f assumes a maximum and a minimum. We are in a setting of a continuous function. The extreme value theorem tells you continuous functions on compact sets have maxes and mins. You did the same thing in calculus 1, except there the compact sets were of this form. Actually, they are here as well. Here's the compact sets we're interested in. But f assumes a max and a min on those little subintervals. Say those extrema occur at x sub I prime and x sub I double prime, respectively. So it was maximum first, minimum second. So the max occurs at x sub I prime and the min occurs at x sub I double prime. Thus, let's look at upper Riemann sum minus a lower Riemann sum. Here's the punchline. We're going to get that that's less than epsilon. And we observed above, I complained about the result, that if you can make an upper Riemann sum minus a lower Riemann sum less than epsilon, then you've got Riemann integrability. It was theorem 6.6 above, an alternative classification of Riemann integrability. So if we look at upper minus lower Riemann sums, we're getting, well, the upper Riemann sums are based on sups of the function over subintervals. Hey, we got a continuous function on compact sets. We don't need sups. We can do maxes and mins. And we know where those maxes and mins occur. So we've got a sum of maximum values times delta x sub i's minus a sum of minimum values times delta x sub i's. If I got a continuous function, I can say maximum and minimum, and I ain't got to go through that supremum infimum stuff that we did above. So write these both as sums and factor the delta x sub I out one side and write it as a single sum. We get a sum of these differences here. How close together are the function values? Oh, I know that because I know how close together the inputs are. How close together are x sub I prime and x sub I double prime? Well, they both came from this subinterval, so they're within delta of each other, as discussed earlier. And when I have x sub I prime and x sub I double prime within delta of each other in absolute value, we get their corresponding function values that small, epsilon over b minus a. So back down. How big are the function values? Well, I know this is bounded by epsilon over b minus a. You worry there aren't absolute values there? Remember, this was a max and this was a min, so I don't need absolute values. This function difference really is positive by the choice of the x sub I prime and x sub I double prime. So I don't need absolute values there, but we can put them there if you like because it's positive. Sorry, non-negative. So we get this difference is less than epsilon over b minus a. We can bring that out front as a constant. You've got the sum from I equals 1 to n of the delta x sub i's. Hey, that's the lengths of the subintervals. That's the lengths of all of the subintervals. Add up the lengths of all the subintervals, you get the length of the big interval, the interval from a to b, which has length b minus a. So this adds up to b minus a. We had an epsilon over b minus a. Those cancel. You get an epsilon. We've got upper Riemann sum minus lower Riemann sum is less than epsilon. Good enough by theorem 6.6 to show that this kind of function is Riemann integrable. Why do we choose epsilon over b minus a up here? Oh, to make this work, to get the cancellation there. So when I reverse engineer it, we could have put any positive thing we want there. We chose to put epsilon over b minus a there because that's what worked downstream in this computation.